If we're going to make use of Chebyshev's bound and other results, that I as an indicator variable means that it's 0, 1 valued. It's also called a Bernoulli variable. And if the probability that it equals 1 is p, that's also its expectation. So we have an indicator variable with expectation of the indicator is p, and we're asking what's its variance, which by definition is the expectation of I minus p squared. Well, this is one of these sort of almost mechanical proofs that follows simply by algebra and linearity of expectation. But let's walk through it step by step just to reassure you that that's all that's involved. I would recommend against really trying to memorize this because I can never remember it anyway. I just reprove it every time I need it. And so let's see how the proof would go. So step one would be to expand this I minus p squared algebraically. So we're talking about the expectation of I squared minus 2pi plus p squared. Now we can just apply linearity of expectation, and I get the expectation of I squared minus 2p times the expectation of I plus p squared. Of course, the expectation of a constant is the constant. So when I take expectation of p squared, I get p squared. But now look at this. I squared is 0, 1 valued. So in fact, I squared is equal to I. And the expectation of I has now appeared here. That's p. So this term simplifies to expectation of I, and this term becomes 2p times p plus p squared. Of course, that expectation of I is a p, so I got p minus 2p squared plus p squared. The p squareds cancel, and I get p minus p squared. If you factor out p, that's p times 1 minus p, or PQ, which is the standard way that you write the variance of an indicator variable. It's P times 1 minus P. Okay, that was easy, and again, completely mechanical. There's a couple of other rules for calculating variance of new variables from old ones that are basic, like additivity of expectation, but it doesn't quite work so simply for variance. So the first rule is that if you ask about the variance of a constant times r plus b, that turns out to be the same as a squared times the variance of b, of r. The additive b doesn't matter, and because the variance is really the expectation of something squared, when you get rid of that constant a, you're factoring out an a squared. And this is the rule that you get here. Okay. Another basic rule that's often convenient, instead of working with variance in the form of the expectation of r minus mu squared, is to say that it's the expectation of r squared minus the square of the expectation of r. Now this expression, the square of the expectation of r, comes up so often that there's a shorthand for it where instead of writing parens, you write e squared of r. It just means the same as expectation of r squared. And so much for the second rule, which we'll use all the time because it's a convenient rule to have. I'm going to prove the second one, just again to show you nothing to worry about. You don't even have to remember how the proof goes because you can reconstruct it every time. So it's again simple proofs just by linearity of expectation and doing the algebra. So the variance of r is by definition the expectation of r minus mu squared. Let's expand r minus mu squared. It's the expectation of r squared minus 2 mu r plus mu squared. Now we apply linearity to that. I get the expectation of r squared minus 2 mu expectation of r plus the expectation of mu squared, if I'm really being completely mechanical about linearity of expectation. Now, expectation of a constant, mu squared, is simply mu squared. And here I've got the expectation of r, that's mu again. So I wind up with the expectation of r squared minus 2 mu mu plus r squared. This is 2 mu squared, minus 2 mu squared plus mu squared. It winds up with minus mu squared. And of course, mu squared is the expectation squared of r. I've proved the formula. Again, as claimed, there's nothing interesting here, just algebra and linearity of expectation. And the first result about factoring out an a and squaring it follows from a similar proof, which I'm not going to include here. So let's look at the space station Meyer again, which we used as an example of calculating mean time to failure. So the hypothesis that we're making is that with probability p, the Meyer space station will run into some huge space garbage that will clobber it. And the probability of that happening in any given hour is probability p. So we know that that means that the expected number of hours for the mirror to fail is 1 over p. That's the mean time to failure. And what we're asking is, what's the variance of f? If f is the number of hours to failure, what's variance of f? Well, one way we can do it is just plug in the definition of expectation, and this will work. The probability that it takes k hours to fail is, we know the geometric distribution, the probability of not failing for k minus 1 hours and failing after that, q to the k minus 1 times p. So the variance of f, using our previous formula about the expectation of f squared minus the expectation squared of f, this becomes a minus 1 over p squared. And we can forget about that. We want to focus on calculating the expectation of f squared. So f is 1, 2, 3, and so on. That means f squared is 149 k squared. The point being that the only values that f squared can take are squares, so we don't have to worry about counting them in the sum that defines the expectation. So let's go look at that. So the expectation of f squared is the sum over the possible values that f squared can take, namely the sum from k equals 1 to infinity of k squared times the probability that f squared is equal to k squared. Well, of course, the probability that f squared is equal to k squared is the same as the probability that f equals k. So I can, and we know what the probability that f equals k is. It's a geometric distribution. So the probability that f equals k is q to the k minus 1 times p. If I factor out a p over q, this simplifies to the sum from k equals 0 to infinity of k squared q to the k. And this is a kind of sum that we've seen before, and it has a closed form. And we could perfectly well calculate then the expectation of f squared by appealing to our generating function information to get a closed form for this. And then remember to subtract 1 minus p squared, because the variance is this term minus the square of the expectation of f. But let's go another way and use the same technique of total expectation that we used before. That is, the expectation of f squared, of the failure time squared, is equal, by the law of total probability, to the expectation of f squared given that f is 1, that is, we fail on the first step, times the probability that we fail on the first step, plus the expectation of f squared given that we don't fail on the first step, that f is greater than 1, times the probability that f is greater than 1. Now, what's going to make this manageable is that this expression, the expectation of f squared when f is greater than 1, will turn out to be something that we can easily convert into a non-conditional probability and find a value for. So the lemma that we're using here is the following. When I'm thinking about mean time to failure, if I think of any function whatsoever, g of the mean time to failure, and I'm interested in the expectation of g of f, and I'm interested in the expectation of g of f given that f is greater than n, that is, it's already taken n steps to get where I am, then the thing about the mean time to failure is that